So here we have a constraint optimization problem in two variables. So we're having a bivariate problem, two arguments. We're having a constraint which involves these two arguments. The somewhat annoying thing about this question is that this function has a coefficient here, a. But note this coefficient is not one of the arguments. So whoever optimizes that isn't thinking about which a should I choose to maximize my function. But that is just the person's problem will depend on whatever the a is. But given a certain a, the person will optimize over x1 and x2. And you can see that in part C we are actually setting a particular value for that parameter. But before that we have to just work with that parameter and consider what values it could take. And it could take values, we're being told that here, that are larger than 0. So let's start looking at this at part A of the problem. Okay, is the constraint compact, and are function and constraint concave? And we know that these are important questions because they will help us to determine A, whether there will be for sure a solution to the problem. That would be if the function is continuous, as this one is, and the constraint is compact. And it would help us to determine whether the Lagrangian conditions we will use later are not only necessary, as they always are, but perhaps also sufficient, which would be the case if both function and constraint are concave. So let's look at this. So let's first look at the constraint. Let's actually have a little sketch here, how that constraint will look on an x1, x2 coordinate system. And you see on x1, x2, we can draw the line by setting that inequality to equal. So then we have x2 is equal to negative 0.4 plus x1. So we have an intercept somewhere here, that's negative 0.4. And then we have a slope of 1. Okay, so that's what the boundary of this constraint looks like. And what this question tells you is we're allowing values for x2 which are on the boundary, that's why we have an equal, or smaller. So the values allowed are around here. Okay, in this area. These are the values allowed. The values not allowed are these ones, is where x2 is larger than that line. And just to make that clear, that actually boundary is also green because we have the equal sign. Okay, it's a closed constraint, we have this equal sign. So the values on the boundary are allowed as well. Now, this constraint is not compact. I cannot sort of capture all the allowed values in a shape, like in a circle, because that just goes on to infinity here on both sides. Okay, so the constraint is not compact. What about, is the constraint concave? Well, we have a linear constraint, and we know that linear functions are both convex and concave. So yes, that constraint is indeed concave. Okay, sorry, I should just make that tick on the constraint. The constraint is concave. What about the function, however? Is the function concave? Now, the function here, you can see it has a cubic term. So cubic functions tend to not be concave, okay, unless something very much overruling it, but this is the highest power is a cubic, so it's likely to be not concave. So if you see that, you can immediately say that. But you could also just look at the Hessian of that function and determine whether that's always negative semi-definite. So I'll just copy down the Hessian of that function. I'm not going to go through the details of the derivation here. Oh, why not? Okay, let's actually do that. We need some of these results later. So we're having the first order partial derivative. That is going to be 3a times x1 squared minus 12x1. The first order derivative with respect to x2 is negative 4x2. And we look at the second order partial derivative, so taking that one and again finding a derivative with respect to x1, so that 2 comes forward, so we have 6a x1 minus 12. Then the derivative of this first order derivative with respect to x2 is 0 because there is no x2. Then we'll calculate the second order partial derivative here with respect to x2, that's negative 4, and that one with respect to x1 is 0 because there's no x1 in here. So the Hessian looks like this. (6ax1 minus 12, 0, 0, and negative 4. So for the function to be globally concave, we would need that Hessian to be negative semi-definite everywhere. So is the Hessian x1, x2 negative semi-definite everywhere? So for all allowed combinations of x1 and x2. So we know for this function to be negative semi-definite, we need the determinant to be positive or 0, and we need the diagonal elements to be negative or 0. So let's look at the diagonal elements. So this second diagonal element, just negative 4, that is always negative. So that's a tick here. But what about this first diagonal element? Well, you can see we know the a is going to be positive because a is larger than 0. And then you can see that clearly there will be some values of x1 where that diagonal element is positive. And if that happens, if we have a positive diagonal element here, then that Hessian cannot be negative semi-definite anymore. So the argument here is no. Yes, there will be some points where it is negative semi-definite, but there will also be other points where it isn't. So the function is not concave everywhere. That means the Lagrangian conditions which we will use will not be sufficient conditions. So let's move to part B of the question. We want to find potential solutions, but these will be functions of A. So that A here, we will just carry that through in our algebra, and in the end we will get solutions where we say, for instance, x1 is equal to not a number, but some sort of function of A. Let's say 6 times A plus 1. Okay? And the same for x2 and potentially lambdas. And only once we go to part C, where we fix the coefficient A, only then we will see what the actual solutions are. So let's start with our work here. Firstly, we have to figure out what is the constraint. Okay, so the constraint g of x1, x2, we need to formulate it in the right way. We need this to be a function which is larger or equal to 0. So you can see here what we're going to do is we're going to bring the x2 over to the other side. So we'll have negative 0.4 plus x1 minus x2. So this is our g function. So what we can now do is we can actually write down the Lagrangian. So the Lagrangian for this problem is the following. So we have our function a times x1 cubed minus 6 times x1 squared minus 2 times x2 squared plus 2, and now plus lambda times, and our constraint function, negative 0.4 plus x1 minus x2. So here's our Lagrangian function. What we now need to do is we need to set down our Lagrangian conditions. Okay, the Lagrangian conditions, and we know in our case they will be necessary, not sufficient, because our function was not concave. Okay, so we need to find, so here they are, okay, it's the partial derivative of L with respect to x1. So we get here 3a x1 squared minus 12x1. That is basically what we just had up here. And now we have a plus x1 here and the lambda, so it's plus lambda. And this has to be equal to 0. Then we're having the partial derivative of our Lagrangian with respect to x2. It's negative 4x2. And then we have the x2 here, and we have a negative, so it's minus lambda. That has to be equal to 0. Then we know that our constraint our constraint, which is just, we have it up here, negative 0.4 plus x1 minus x2 has to be larger or equal to 0, and then the complementary slackness condition, which says that lambda times that constraint has to be equal to 0. So here are our 4 conditions. How do we go about solving this problem now? Well, let's first, as we usually do, let's try lambda. I'm going to use a different color. Let's try lambda is equal to 0. Okay, in that case, our conditions simplify, because we can take that first one and we get 3a x1 squared minus 12x1 is equal to 0, and the second one will deliver minus 4x2 is equal to 0. Okay, so we can immediately see that from here x2 has to be equal to 0. But what about the first one here? So we're having a quadratic equation in x1. You could immediately apply a quadratic formula, but since there's no constant term, it's much easier to just factor out an x1. So we get x1 times 3a x1 minus 12 is equal to 0. And from here you realize that for this product to be equal to 0, it's either the x1 which has to be 0, or it's this term in the parenthesis which has to be 0. So we know that x1 is equal to 0, or 3a x1 minus 12 is equal to 0. And from here you can learn that we can solve that for x1, and what you get here is that x1 is equal to 4 over a. Okay, so as we said, because we are having this coefficient a in our function, we said the potential solutions will be functions of a, and so here we have that a in the solution. So basically what we've established here is that there will be 2 points, okay, and let's call them point A, where x1 is equal to 0, we got that from here, and x2 is equal to 0. So let's say x1 is equal to 0 and x2 is equal to 0. That's one point. And we have point B, where x1 is equal to 4 over a, and x2 is still 0, because x2 has to be 0 for these 2 equations to be true. So we have 2 points. Okay, so now one question is, whenever you try and solve for lambda equals to 0, you're temporarily suspending the constraint and solving the problem as if it was unconstrained. But now we have to remember, well, yes, there is a constraint. So we have to check whether these 2 points meet our constraint. So we'll calculate. We take our constraint equation here. So we'll take negative 0.4 plus x1, which is 0, plus 0, minus x2, which is 0, and that is negative 0.4. But remember, our constraint function has to be larger than 0. So this point is not valid. This point is not allowed because it is smaller than 0. It's not allowed by the constraint. So what about point B? So let's do the same. So point B, we plug these coordinates into the constraint. We get negative 0.4 plus x1, which is 4 over a, minus x2, which is 0, so minus 0. So what is this? Okay, so basically what you see here is that you get negative 4 plus 4 over a. So let's actually, so we need this to be larger or equal to 0. We can bring the negative 0.4 on the other side. So you get 4.a is larger or equal than 0.4. So whenever 4 over a is larger than 0.4, then this point is allowed. So what does that mean? We have potentially an unconstrained candidate solution, but that depends on what the value for our parameter a is. So you can see if that a is actually so we need this to be larger, so we need small sort of a's. If that a is actually smaller or equal to 10, then this point B will be allowed. Okay, but if a, for instance, was 100, we would actually get 0.004, and that would be not larger than 0.4. So whether this is allowed, point B is allowed or not, will depend on the A. So let's move on. I'll move this up here, and let's try, and which color shall I use? I'll use orange now. Let's try lambda larger than 0. Okay, so you can see our problem here. So let us now write down what the Lagrangian conditions are. So they are now 3a x1 squared minus 12x1 plus lambda is equal to 0. Then we're getting this one here. So we're getting negative 4x2 minus lambda is equal to 0. Now we have three unknowns, x1, x2, and lambda. We need a third equation. We get that from the complementary slackness condition. If lambda is larger than 0, then g has to be equal to 0. So this inequality constraint turns into an equality. We're now looking on the boundary. So it's negative 0.4 plus x1 minus x2 is equal to 0. So now we just have to use a little bit of algebra to get here. So you can see that these two first equations, we can solve them both for instance for lambda, okay? Or we could, you see that first one here turns into, if I bring the lambda on the other side, it turns into negative lambda is equal to 3a x1 squared minus 12x. And if we solve this for negative lambda, let's solve the second one for negative lambda as well. So that's negative lambda is equal to 4x2. And from here, we learn we can set the two right-hand sides equal to each other. So we get 4x2 is equal to 3ax1 squared minus 12x. Okay. So from the constraint, you can also learn, so we have an equation in two unknowns. Sorry, that was 12x1. I forgot the x1 here. Okay. An equation with two unknowns, but we have one equation with x1 and x2, and down here we have another equation with x1 and x2. So we can, for instance, solve this one, the constraint equation for x2. We get that's negative 0.4 plus x1. And then we can substitute this into this equation here. So we get, so if we do this, we get 4, and now instead of x2 we are having negative 0.4 plus x1, and that is equal to 3a x1 squared and 3a x1 squared minus 12x1. Okay, now we have an equation, quadratic equation in x1. We can simplify that to bring it into our favorite quadratic equation form. I'll jump a few algebra steps, but what you'll get is this: 3a x1 squared minus 16x1 plus 1.6 is equal to 0. So now we can apply, you can apply your favorite quadratic equation formula, but remember, there is still this parameter a in here, so we'll have to carry this in our calculations. Okay, so our factor to x1 squared is 3a, not only 3. That means it will appear in our equation. And what you get if you do that, and again I'm jumping some steps, I'll expect that if you look at this video you know how to solve quadratic equations, so please make sure you can replicate this. We're getting 16 over 6a plus minus, we know we have potentially two solutions, and then the square root of 256, which is actually 16 squared, minus 19.2 times a. So here's the a again. So the a now appears in a number of places. Okay, so here is our formula for x1. That gives us two solutions for x1. Okay, and once we have x1, we know what x2 is, because x2 is just x1 minus 0.4. So what we can do here is we can just basically say we have two potential extra values, but you can perhaps already see that you know that for us to find solutions here, we need this square root to be or the argument to the square root 256 minus 19.2a, that cannot be negative. So if this is negative, then there will be no solution in this section. Okay, and you can see when this will turn negative. That will turn negative for very large values, or for large enough values of a. You can actually figure out what that is. It turns out that if a is larger than 13 1/3, so 13.333, then this pink highlighted term will turn negative, and then we will get no solution from on our boundary. Okay, but if a is smaller than that, you will find a solution. So let's just say, what will these two solutions potentially look like? Let's call them point C and point D. So C and D now differentiate by whether we use the plus or minus in here. So at point C, let's use the plus, it doesn't really matter. Okay, so here x1 will be 16 over 6a plus the square root of 256 minus 19.2a divided by 6a. In D, we'll just take the minus value. Minus, and now this somewhat nasty looking term divided by 6a. And now x2 is always just x1 minus 0.4. So I'll just say here x1 minus 0.4, so I don't have to repeat this long term. Okay, so what we now also remember, whenever we are looking at values on the boundary, we also need to figure out what the lambda value is, because the lambda value has to be larger than 0. Okay, all the lambdas have to be larger than 0. I forgot to state that here, actually. I should state it here. Okay, lambda has to be larger or equal to 0. So what is the lambda? Well, we know from here, for instance, that's possibly the easiest relationship for lambda. We know that lambda is negative 4x2. Okay, it's negative 4x2. Here the same, negative 4x2. So we can see that if x2 is positive, then lambda will be negative, and that will not be allowed. Okay, so whether x2 is negative depends on x1, and what we have for x1 depends on the a. So we can't actually generically answer the question at this stage. Okay, we will have to see for what the values of x1 and x2 will be. Right? Basically what we need is we need negative values of x2 so that the lambda is going to be positive or 0. Okay, so we'll go now to part C to actually complete the solution, because we can't really go further at this stage. So let's just briefly go up and see again what part C looked like. So what we've done basically is we've considered our potential solutions. Okay, and let's summarize what we found. We found that when we are looking for potential solutions in the unconstrained part, there is a potential solution B, although we already figured out that for B to be a potential solution, the A cannot be larger than 10. Okay, but if the A isn't larger than 10, if the A isn't larger than 10, then B will indeed be a potential solution. Then what about the constrained part? The constrained part, we found 2 potential solutions. Whether they'll be allowed, i.e. whether they have lambdas larger than 0, will depend on our A. Okay, and then also once we have that, we can then compare the 3. So we're at this stage, we're still having 3 potential solutions. Okay, and once we have the A, we can then also calculate function values and see which ones of these is the best. So now part C of the problem now gives us a value for A. Let's say A is equal to 4. Okay, so let's move on with our problem and say and set. So part C here, A is equal to 4. So that means we can now actually look at our 3 remaining potential solutions. Okay, let's look at point B. Okay, at point B, we know that x1 is equal to 4 over A. So 4 over 4 in our case. So x1 is going to be 1. And x2 is always 0. Right? So x2 is always 0. So here our point is 1 is 1, 0. Is the constraint met? Well, if we go back here, we have negative 0.4 plus 1, which is equal to 0.6, which is larger than 0. So at this point, this is allowed. Okay. Now we will also need to eventually compare to potentially both C and D. We will need the function value at 1, 0. Now remember, to calculate the function, we can actually calculate the function because we now know what the function is. The function is now, the function x1, x2 is now equal to 4 times x1 cubed minus 6 x1 squared minus 2 x2 squared plus 2. So if you plug in 1 and 0 into that function, what you will find out is that the function value here is 0. So let's move on to point C. So we look at point C. Now what about x1? So you can now plug in, remember the A, where the A appears. The A is here, here, and here. And of course here, here, and here for D as well. We can now plug in our value of A equals 4. And if you do so, you get, and I'll spare you me typing on a calculator, but you can confirm that, is 1.2244. x2 will be that value minus 0.4, so that will be 0.8244. And then we know what the lambda will be, because it's going to be negative 4 times x2. So lambda is going to be negative 4 times 0.824. And really all we need to know from here is that that lambda is smaller than 0, because it's negative 4 times something positive. That means for this value of A, C is not a candidate solution. So let's move on to D. So if you plug a 4 into that, what you will get is that x1 is equal to 0.1089. Then x2 is going to be that value minus 0.4. Okay, x2 is x1 minus 0.4. So we get negative 0.2911. Then we can calculate lambda, which is negative 4 times, that should be 4, negative 0.2911. And really all we are interested in is that this is larger than 0. So D is a potential candidate solution. We have B and D. Now we need the function value at that point. So we can plug in these two coordinates into the function. So again, after a session with your calculator, you will find that the function value here is 1.7645. So that means if you compare the two function values here and here, we know that the candidate solution which remains, because it has a higher function value, is this one. Okay, D is our remaining potential solution. So let's summarize. We formulated our Lagrangian conditions here. We found potentially 3 points, B, C, and D, which would meet these Lagrangian conditions, depending on what the value of A was. Then we fixed a value of A as part of sub-question C. We fixed the value of A to be 4. That meant point C dropped out, because at that value it didn't meet the Lagrangian conditions any longer. We had 2 points, B and D, which both met the Lagrangian conditions. And what we then do is we find out which of these 2 points is better, and that was point D because it had a larger function value. Now, since our Lagrangian conditions are only necessary conditions, we know that if there is a problem to the solution, it is point D. But we haven't yet established that this is the solution to the problem. So why is this? Recall I'll move this here. And I'll just copy the constraint again. The constraint was gx1, x2 was that negative 0.4 plus x1 minus x2 was larger or equal to 0, or it was x2 is larger, smaller or equal to negative 0.4 plus x1. So let's again have a little sketch, a little larger now. Okay, I hope in my recording I didn't cover my face, didn't cover anything. So we know the constraint was here was negative 0.4, and then we had a 45-degree line because the slope was 1. And the values which were allowed were the values here to the right. Okay. So let's see where our points actually were. Point B was 1, 0. So that's negative 0.4. So 1 is about here. Okay. So this one here was point B. What about point D? Point D is somewhere here. Okay. About 0.1 for x1. So this was 1, 0. And negative 0.3 for x2. So this one here was point D. Okay. So now we need to know, and we know that the function value at point D is larger than the function value at point B. What we now need to figure out is, you see the function, it can move into all sorts of directions here. It can move into this direction, can move into this direction, down here and down here. So we need to, and of course up here, we need to establish how the function behaves into these directions. So let's start with, let me do this purple, let's start with this direction here, because that's a nice partial function. That is the partial function where we allow x1 to go large, but we set x2 equal to 0, okay, if we are going along this axis. And what we are basically asking is, what is the limit of that function as x1 goes to infinity? So we have our function here. If we set x2 to 0, we get 4x1 cubed minus 6x1 squared. So actually what I should do, sorry, let me rub this away. I just need some space. So we are asking, what is the limit as x1 goes to infinity of, and now what I had before, 4x1 cubed minus 6x1 squared. So now you see, so we have a cubic term which is positive and a quadratic term which is negative, but the cubic term is going to dominate the quadratic term. And so x1, if x1 goes to infinity, this term will go to infinity. This one as well, but this term will go to infinity faster than this. So this is just infinity. So as the function here moves into this direction, the function will actually go to infinity. And here is our answer. At point D, we found a local, basically a local optimum of 1.7645. But since the function in an allowed area shoots off to infinity, this is not the solution to the problem. This problem has no solution. There is no maximum, because we can always find larger values by, for instance, walking along that axis and always increasing x1. Okay? So, let us briefly recap how we ended up here. We ended up with our last remaining candidate solution, point D. But since our Lagrangian conditions were not sufficient, we actually had to investigate the shape of the function in the allowed area, and we discovered that in some part of the function shoots off to infinity, goes beyond the function value at our candidate solution, which was just 1.7645. So the function here in this area goes beyond that value. Therefore, there's no solution. And that's the answer to the problem.